the role of contractility in cardiac function. Cardiac output relies on the regular contraction and relaxation of cardiac muscle and is tightly controlled by a multitude of neurohormonal compensatory mechanisms that modulate heart rate and affect stroke volume. Under pathological conditions, compensatory mechanisms can become maladaptive, contributing to diminished systolic function and reduced stroke volume, the hallmarks of heart failure with reduced ejection fraction, or HFrEF. Although the development of HFrEF is complex, the primary myocardial defect is impaired contractility, driven in part by changes within the fundamental contractile unit of the cardiomyocyte called the sarcomere. Each sarcomere comprises repeating bundles of contractile proteins, including myosin-containing thick filaments and actin-containing thin filaments. In non-failing hearts, contraction and relaxation of the sarcomere is the result of cyclical interactions of myosin with actin that are coordinated by a precise cycle of calcium release and reuptake. The binding of calcium to regulatory proteins exposes myosin-binding sites on the actin filament. Independently, the myosin head hydrolyzes ATP, becoming primed. The primed myosin head binds actin, first weakly and then strongly, creating a crossbridge. The release of phosphate causes the myosin lever arm to swing, generating the power stroke that slides the thick and thin filaments past one another. Upon ADP release, ATP rapidly binds myosin, causing the myosin to quickly dissociate. As the ATP is hydrolyzed, the myosin lever arm returns to its primed position, ready for the next contraction. Cross-bridge cycle kinetics allow many myosin heads to work together, generating force to shorten the sarcomere. In HFrEF, complex changes to cardiomyocyte structure and function affect contractility. Abnormalities in cross-bridge cycling result in fewer myosin heads interacting productively with actin during systole, contributing to diminished force of contraction. The cumulative effects of these changes reduce cardiac contractility, resulting in a decrease of overall cardiac function, including decreased time in systole and diminished cardiac output seen in HFrEF. In general, the current standard of care treatments for patients living with HFrEF target maladaptive compensatory mechanisms, but residual risk remains. Additionally, traditional inotropes, also called calcitropes, that augment myocardial force by increasing intracellular calcium concentration are only recommended for short-term use. Treatments have come a long way in addressing the effects of maladaptive compensatory systems seen in HFrEF, but more can be done. The mechanism of myocardial contractility is an area of great interest in heart failure research.